still do it this way. So let's, as we go line by line, let's see what the contents of the stack looks like, and then at the end, we'll find that it is a parenthesized equation, so that we'll be able to, do something similar to if you wanted to have 8 plus, and then some numbers in parentheses, and then times some other numbers. How would you do that implemented using a stack with just push and pop as the commands? That's what we'll look at. So all the commands are here. So let's just write little comments on the side, and then at the end we'll see if it matches up to the comments that we write. So hopefully I put the comments in correctly. So if I do something that doesn't seem copacetic, just ask, and then I'll take a look and we can correct it. Okay. Right. So obviously the first one, push 5. What is the contents of the stack? 5. So the only thing that you're ever going to think about is what's been pushed onto the stack. That's the only thing that can possibly be on the stack. So we got push 5. So stack contains 5. So now push 9. So remember, there's no operations that go on unless you put in a multiply or a plus or something. You're just simply making a list of numbers that is in the form of a stack. So now the stack contains what? Yes?
Well, if you push 9, then you're pushing the number 9 into it, right?
Yes.
And then the next one you push 8, but when you push inside 2 pops, you're pushing out...
Well, no. Forget, never read ahead, ever. Like, no matter what you're doing, never read ahead. What's the one line that you're looking at?
Alright, so we're looking at line 8.
So push 9 does what?
It adds 9 to the stack.
So then, what does the stack contain in total?
5 and 9.
5 and 9. And if we were going to look at the top of the stack would be what?
5.
So stack is last in, first out. So I put a 5.
So 8 then will be in the top.
No, after this line.
9.
9. Because the last one that you put on the stack is the one that's at the top. So whichever command has last been executed, that one represents the top of the stack. So then the next one we have push 8. So now we have the stack being 5, 9, and 8, with 8 being the top of the stack. So not a whole lot of surprise here yet. Well, probably won't be much surprise at all. Let's look at this methodically. So we have 5, 9, 8.
But then I thought 8 would be on the top because you said the last one you put in was on the top.
It is. So 5, 9, and 8, and I'm representing the one that's at the right side as the first. That's my way of doing it. So then the next one says push, and then it says push 2 pop commands. So if the top of the stack has which number in it again? So
It has 8.
8. So when we execute the first pop command, what's going to come off the stack?
8.
So 8 comes off, it's popped, but it's being, when you include a pop command inside of a push, you are essentially popping it off but then pushing it right back on. So if we were to simply say push pop, we would be taking 8 off and putting it right back on. There'd be no difference. But here we're doing pop and then plus another pop. So if we're doing 2 pops, which 2 numbers would pop off the top?
8 and 9.
What's that?
8 and 9.
8 and 9. So pop and then plus the other pop. So this is now pushing onto the stack, popping off 8 and adding it to popping off 9. So that push pushes what onto the stack?
17.
What's that?
17.
17.
Wait, how do you get 17?
Because we're popping off 8 and 9, and then it's saying when you pop them, add them together, and then push them out. So add them and then push the result of the addition back onto the stack. So now the stack contains 5 and is 17. However, if we write it out as an equation, we can write it out as 5 comma 8 plus 9. And I write it as 8 plus 9 only because however you write it is kind of arbitrary, because from what I've read about the internal structure of a x86 computer, the order of the pops is random. Believe it or not, I didn't get a chance enough to try it. I was trying to get it to give me a wrong answer where I had a subtraction. But from what I've read, some of the implementations, when you do this, it might pop 8-9 or 9-8. So that's why I don't make the order very specific. But I haven't been able to generate an example yet. From what I've read, that's the case. So now we have 5 comma and then 17. But we're doing this to generate an equation at the end, which will have several levels of parentheses to show how your calculations are done on your computer or in a calculator. So now we're at that stage. So now we go to the next one. So we got push 4. So if we push 4 on, what will the list of the stack be? Nevada, what will the list of the stack contain if we push 4? Here's the stack right now. Can you read it? So what will the stack list contain if we push 4 on? So what's that?
5, 8, and 4?
Yes. Well, 5, 8, 8 plus 9, and then 4, yes. So 4 is the last one because it's being pushed on. The last one in is the top of the stack. Last one in, first one out.
I thought 6 was the last one in.
We didn't push 6 yet.
Okay.
So we have 5, comma 8 plus 9, comma 4, and now push 6. So we have 5, 17, 4, 6. So I will continue to write it like this, though, so that we see the way that the equation is slowly being built. So 4, comma 6. Okay, so now we have 2 more interesting situations where we push on 2 pop commands. So the next one says pop and then pop another one, but multiply them. So what are the 2 top values that are in the stack now? What are the 2 pops going to be? What individual numbers? Julia?
I'm gonna take a look at 4 and 6.
4 and 6.
Oh, okay.
So it says pop 4, pop 6, multiply them together before you put them back on the stack. So I'll put that in parentheses as well. So we'll now list the stack contents as this. So now we'll have 4 times. Okay. So now here's our stack, and we can see that we're developing, what could be an equation once we finish up. So the next line now also says make 2 pops off the stack and then multiply them together again. So remember, this is actually a 24 and this is actually a 17. I just represent it as the original equation so that we see that this is actually a calculation that's built up by a series of pushes and pops. So if we pop 2 things off, what 2 things will pop off now?
17 and 24.
17 and 24. So it says pop and pop again, so we're going to do 17 times 24 because it's saying to multiply both of them. So we'll do this. So let's just get a running guess of the numbers here. So let's see. so now push 7. So right now the stack has got 5, comma 408, nothing else. So now push 7. 7 will be the top of the stack. So we'll have 3 elements. But I'm going to continue to use these parenthesized equations. So we have that, and then we have our 7. So this looks like this because this number is actually 408. I've just left it as parenthesized equations to show that we went from this and this, multiplied them, got that. So now the stack is 5, comma 408, comma 7. Okay, so now we've got this one. So this says again to make 2 pops but add them together. So which 2 numbers are going to be added together when we're doing those 2 pop commands off the stack? 408 and 7. So let's put that in. So we've got this, that. So 7 plus 408 is 415, so we've got this and we've got that, but the extendable equation is still this. So the 5 is still, notice the 5 is still sitting at the beginning of the list. It's never been accessed because we never got down that far in the stack. So that's why you have to figure out when the stack is best, just like having a stack for the inboxes they used to have in offices when they were more paper driven. If you had an inbox and you had the top papers be the ones that were first attended to, the ones at the bottom might never be touched. So always realize that the stack has this property. If you want to have the values always to be attended to, then you use a queue, which is like a stack, but it's first in, first out, just like a line you get on for registration or something like that. So now we have another push with 2 pop commands being multiplied by each other. So which 2 things will be multiplied? There's really not too much room for.
Oh, it's 5 and 415.
Yeah. So we're going to multiply 5 times 400. So let's just do that. So it says 2075, because we have 5 times 415 equals 2075. So those 2 things are put back on the stack. So then the final one is just print out the stack by popping off the value. I suppose we could, we can do that, and we can also just print the stack itself. It should be the same thing. Both should print out 2075 because there's only one element on the stack. But this way or the other way, this way would give you a different answer than printing out the stack itself if there was more than one element. But in this case, there was one missing. So we've got our equation now. So before we run it, let's just see what our equation looks like. So we've got the equation that looks like this. Okay, so last one we had pop off 5 times 415, so that was 5 times all this. So if we do 5 times everything here, we have to put parentheses around that equation after the comma. So now you'll see how using consecutive pop and push commands generates a parenthesized equation. So it's the same as doing this. So notice that just by using some pushes and pops, we generated this more involved looking equation, and we should get 2075 when we pop off the last value. So let's see if that works. So we're actually going to see this command run. And that's what we get. So again, this is just to give you an idea of how to trace through a program and see what the value of each output is. And you can just put a print statement of printing out the stack at each step, and then you would see the stack. For example, if you wanted to be sure that that at this step the stack really was 5 and 415, you can print the stack out there. And you can do that at every other situation as well. And then we see the contents of the stack. So you can do that to inspect the inner workings of the stack for yourself, and then use the pop command. You can also print the pop command. Let's see. Let's try out whether or not we can print the push command. I'm not sure if you can, so let's try it. Okay, so it looks like it's going to at least try. So when we do calculo push 7, we should see 5, 408, 7. If everything was going as according to our estimations. Actually, wait. Yes, it is. I was only printing the push. So this is interesting, because I wanted to see whether or not it gave us the whole stack, or it just gave us the single push and it gives us the single value. So there's not a whole lot of information that we got from this one, because it didn't give us the whole stack. It just gave us pushing on the 7. Whereas if I do the print command and print the whole stack right after, we should see 5, 408, 7. So let's just verify that, and then we'll make that the last layer. So we got that. So SAC is pretty. Once you get the idea that the last one that's pushed on is the one that's at the top of the stack, and that will be the one that's first removed when you issue the pop command, then the stack is pretty handleable as a data structure. Let's see. Anything else for the stack? I don't think so. So, going back to the idea of recursion, let's take a look at the difference between the subtraction and the addition recursion. We haven't done subtraction. Maybe Sanchita did it with you, but did she? Recursion? What? Did Sanchita do the subtraction version of recursion?
No.
So let's take a look at what that is. So. Go to 12. Okay, so let's start out with the add program. I've got subtraction hanging around somewhere, but let's look at the add program itself. So we've got A plus B equals something. So let's look at what the recursive call did again. So down in the recursive call, this says for A and B, add 1 to A B times. So if you want to add 7 to 10, you want to add 1 to 10 and do it 7 times. So that's the purpose of this plus 1. So based on that idea, what could possibly be a way of doing subtraction?
We can change that +1 to a -1, and then
We
you
can
switch
do
back.
that. So let's try it. So based on if this is 10, this is 7, and then loop it down to the base case, add 1 to 10 7 times. Let's try subtracting 1 from 10 7 times. So first let's run it, make sure it's in working order for addition before we do any changes. So let's make this 10 and 7. Okay, so 10 added to 7 is 17. So now let's try changing our recursive call simply to a -1, which will or may have the effect of every time that we loop through, B times subtract 1 from whatever A is. So let's make A 20 and B 5. So let's subtract 1 from 20 5 times. So let's see if we get 15 back out of this. I have to change the text, obviously, if we wanted to stick with this, but we see that it did work. 20, ignore the words, but we took 5 from 20 and we get 15 because it's simply removing 1 at each step instead of adding 1 at each step. So the difference between addition and subtraction is pretty straightforward. So that one is pretty easy. So let's take a look at multiplication. So multiplication. For multiplication, we had the recursive algorithm where we said x plus x times. So with the addition, there was no variable here. This was like a 1. So it was like 1 plus that. So if we change this to a 1, this is addition. But instead of adding a 1 every time that it loops through, we're adding the number itself to itself as many times as you want to multiply by the other number. So if we want to multiply 5 times 4, we're adding 5 to itself 4 times. Just like we added a 1 to a number as many times as you wanted to have added to it. If you want to add 4, you added 1 to the number 4 times. But if you want to multiply by 4, you take that number and add the number to itself 4 times. Then you decrement down to the base case. So let's run it, make sure it works, and then see if we can do the same easy thing for division. And there are different ways to do recursive division. I'm not sure the way that I did it, so we'll try it the straightforward way, and if it doesn't work, we'll take a look. So let's go up and look at what numbers we have. So we have 5 times 4. So we should get 5 times 4 is 20. Okay, so 5 times 4 is 20. So using the same logic as before, Diego, I saw you talking to Maxim and saying you got this already, so what would you guess could be one change to make this to division as a guess? It might not work.
I don't know what.
To change this from division, from multiplication to division, what one change, one character change, can we try at least?
Or you want to change it from division
We want to change it from this being, this result in multiplication. We want to make it into division, just like we changed the addition one to subtraction. So, using the same strategy, what could we change?
get times, not multiplying.
We still, well, that's only the name of the method. Always remember, the name is not too crucial because we make that. So either a variable to a number, or change a sign from minus to plus or plus to minus.
We can make it 1 over when you're multiplying by.
Make it what though?
Put 1 over the factor that you multiply by, so that it's by.
Well, let's just see if there's even a way to do that. Let's see.
What if we change that plus to a divide or minus?
Well, that's what I was going after,
Plus to
but I
minus?
want to go with Diego's idea for a second to see if there's a way to even try it. So if we wanted to do division, and we did x plus. Right, so the only way to get division to work would be to somehow make a number a negative number. So
Do
I don't
minus-
think I can think of a way to make yours work.
Oh, minus x times.
But yours, I think we can. We'll try it and we'll just see what we get first. So we're going to do minus. So we're going to do subtracting x from itself n times. But let's just think about it. So we x is 20, x is 5, and yeah, let's use something more divisible. So let's do 50 and 5. Okay, so 50 divided by 5 is 10. So let's just change the values before we do it. But first we'll think about it. So we're doing 50 divided by 5. So if we do 50 divided by 5, that'll be 50 minus 5. No, 50 minus, yeah, this wouldn't work too well. Because see, in this case, well, let's try it and see what comes out, but that's why I was saying when we first looked at this, there are several ways to do recursive division, but I don't think this is this way will work. Let's try it, and we'll see why. Let's just change.
It does not work.
Yeah, well, it doesn't work. If you think about it, like the first way we had 50, if we were going to do 50 times 5, it would be 50 plus itself n times. So if we change back to a plus, it'll work again because it will take 50, add 50 to 50, that's 100, add 50 again, that's 150. So we'll get 250 because it's adding 50 to itself n times. So let's just make sure that we didn't change our algorithm and that it still is working, and then we'll look at what we were trying to make it do. So it still works. 50 times 5 is 250. So now we look at this and we were trying to say 50 minus something n times, but if we subtract 50 from itself, then 50's gone in one shot. So that way it's not going to get us to our number, because we know inside that 50 divided by 5 is 10. So we need to somehow get a 10 out of this. So let's take a look at the recursive division and compare it to this. See if there's even any analogy. So let's do 50 and 5. Let's make sure this works. So here is our recursive division algorithm. So it says, so x is 50, y is 5, so 50 divided by 5 is 10. So the recursive call is x minus y, y times. So notice that that's the key difference we wanted to get. We wanted to have 50 having something subtracted from it, but it couldn't subtract itself from it, because then you get 50 minus 50 is 0. We know that's not the answer. So if we do 50 minus 5, then that's 45. 45 minus 5, that's 40. 40 minus 5 is 35, etc. So you subtract whatever the other value is. You subtract it from the one that you want to subtract from, and you subtract it that many times. So we're going to subtract 5 from 50 5 times. Does that make sense? 5. Let's just write it out, because obviously that is the way it's happening. But let's just see if it works in a series of comments. And also, we can do, let's do an inspection. Let's just put a print there. So instead of doing the whole thing, let's just print out x. So x is x. Okay, so we got okay, so we got 50 and 5, so we want to divide 5 into 50 to get 10. So here we've got the operation happening here. So before we do an analysis, let's just compare this in the abstract to multiplication, to show that in this case there really isn't too big of a difference. I mean, there really is a very large difference. So we see, can you see this? In the back? No, we'll try to get it. So comparing multiplication and division, we see that with multiplication, it is unlike comparing addition and subtraction. With addition and subtraction, we simply had changed the +1 to a -1, and it made subtraction out of addition. But in this case, that doesn't work simply because of the properties of division. But everything, again, in computer science is mostly based upon addition. So this is still based upon addition here, because instead of adding x to itself, we're adding a -y to x. So that's a way to think about it, because most operations in the processor happen from an add. So if you see x minus y, that's the same as x plus minus y, and you do it y times. So you're doing something similar to the reverse of addition, where we're taking away a 1, but in this case we're not able to do it with the x itself, because that doesn't give us the operation. So it's just that the lack of symmetry makes it not as fun, but it's not very much more involved either. Oh, I know something. I realized I didn't post up the PDF on this yet, so sorry about that. But let's just take a look at this and see if you can make a guess at something, and then we'll talk about why it works both ways on the way back from break. So the GCD algorithm from Euclid, if you have greatest common denominator of 30 and 5, 30 and 10. The GCD of 30 and 10 would be what? Like the largest number that they both share in factors. 30, they have 6, 5, 3, and 10. What factor is the largest factor that 10 and 30 both share?
5. I didn't count.
No, I was actually thinking the wrong one, but not that one. So, but then I thought another way when Jack was saying at me. So, yeah. So 30 GCD of 30 and 10, 30 and 5, 30 and 10 will give us 10. But then if we do 10 and 30 using this algorithm, let's see if we still get the correct answer. Meaning, do we still get 10 if we put them in as xy or yx? And will this algorithm work both ways? And you can either try it during the break, or just guess during the break, or quickly look it up and see if you want to talk about the explanation. So let's use 30 and so geez, 30. Okay, so we get 10. So now if we do GCD 10, 30, let's see if we get that same answer.
I'm guessing it doesn't work. Oh, it does.
So it does work because if you do x mod y, if you take 10 and divide, and then you mod, like if you, to leave that aside, if you do 5 and you say 5 mod 3. If it's not going in evenly, mod gives you the remainder. So 3 divided into 5 is once with what remainder?
1.
Yeah.
No,
3
2, right?
2. So 5 mod 3 will give you 2. So, and then remember, if the number that you're trying to mod into something is bigger than the number, then you just get back the larger number that you were trying to divide into. So 10 mod 30 means try to divide 30 into 10 and tell the remainder. Since it won't work, that means that it returns back 30. So if you put 10 comma 30, it has the effect of switching the variables. So I guess I'm giving it away. So if you write in 30 comma 10, it works and you expect it to. But if you write 10 mod 30, 10 mod 30 gives you the remainder of 30. So then when it runs the algorithm again, it's 30, 10. So if you put them in the opposite order, it just switches the placement because of the way that Euclid's algorithm works. It's like kind of built into the calculation. So that's why you will get the correct answer either way. So let's do a break and then we'll come back and we'll see if we can do a print statement of that. I'm not sure if we'll be able to see the swap action, but we'll try. So let's do a 10-minute break. For anybody that came in later, for the final you'll be able to have your laptop on you because I was given some common questions from the department that I want you to be able to have a compiler on you, so you can have a laptop or a tablet or a phone or all three. Just don't talk to anybody. If there's any evidence of shenanigans, then they'll give you trouble. Of course, trouble meaning you get a bad grade, which is like the worst thing in the world for me, so don't do that.
Professor, are these posted on Blackboard?
The review slides are posted.
Yeah, I'm trying to get the division in. That's alright.
Well, I'll put the code out. I'm just trying to
Thank
look
you.
on my laptop. I was trying to get the Zoom to happen fast, but it said to use the num key as your quick toggle key, and it's not C and num key. Like on a full keyboard, you know what it is? It's not visible. That's what I was looking for. So I'll put it back.
Okay.
You read?
I'm saying, like, you know how there's like 3 credit cards? You might have like 2 credits on. It's like 7, because usually it's like 3 and it's like 6 credits.
I'm heard of I know. Let me get the changes to me.
I don't know what it is. My voice is so weird today. I'm like, testing.
No, because I was busy doing
I was in history. Is it ready?
the hardest choices acquire the strongest wills.
I can't even read. Is it really?
Hold on, I gotta scroll this up. This is smart board. No, this is Chris, don't do anything there. Chris, don't change it. Scroll up and show me comes back in.
I don't think you can even add them if you're
I've highlighted this. Sneak 100.
Take yours and shake
What? Wait, where?
If it controls Z,
We're recording G's.
if it controls Z for a
You
second.
motherfucker.
No. Yeah? Yeah.
This is all I got, look, CIS and INT.
Yeah.
Are you taking
INT.
this is all I have?
Yeah.
Which one are you taking?
You know, Chris, because of this, I think I'm gonna track keystrokes now, so I know what to do with stuff when I'm gone.
I think it's just because.
Make it, it's making me fucking track your my own goddamn keystrokes.
I usually
Sometimes
look
they
on
don't
schedule
show.
like
Yeah.
before.
Like, look up on schedule.
Why you gotta make me track my own goddamn
Sometimes they would be
keystrokes?
in our community, but like it won't be INC, it'll like be
Oh,
under.
man, she got one of those artificial intelligence, like, APG storage group, right? She goes,
This hearing, one of them, they just broke the other one, so they like even out. Like I didn't know, I was like, oh, I'm going back, I didn't know what the piece was.
What the hell did you say?
I was like, break it. I really still there, I was like, I was like, break in this exact spot, please.
yeah, these are all like.
Yeah, see, like sometimes it goes like in that hard, like it goes under a department. That's not true.
Chris, you did something else.
Did what?
You did something else here.
No, I didn't.
I know you did something else.
Which subject? All subjects.
I mean, that's just what I did.
That's kind of weird.
You did something else, Chris. You fucking did something else.
Oh. Sorry. I just forget your idea. Like idea.
What are their new replies for?
And like an interface. Oh yeah, I was like I was helping
Oh.
Brian out, but like he accidentally posted my name because it was on the other one.
Okay.
What the fuck did you do, Chris?
I didn't do anything.
I don't know. It's just like a thing to clarify.
Yeah.
No, but I've seen that idea somewhere else.
Fuck, dude, these trademark.
I don't think it's a trademark.
I think steal it. Just because I feel like it's
Yeah.
Must ask the shady worker for an iPad checking the picture in the bag with the key code. This being a Walgreens.
Uh,
If anyone doesn't have the division recursive code, I put it inside in the game.
Well, it's you.
I didn't realize that's it, but I was like, yeah. We should go to the bathroom. Some other lady asked you to not get access.
okay, the body's right here.
Another week. Choose random dinner. So like, let's just set up a dinner.
Yeah.
What do you went to?
There's one called Border Crossing Migration and American Society. It's a sociology.
You're a socialite.
I really need to learn how to do all that. I'm such a good idiot. Maybe I should just
That would really wreck my.
Did you send the link?
What link?
Thing?
He's right my conclusion.
Oh god damn it, the the audio still. Shit. Well, it only makes us class people more human. Ooh, funds are now available. Thank you so much.
Guys,
Rip.
the lady called me a stupid
Earlier.
Who?
man.
Huh?
What?
Oh, wait, what?
Yeah.
Diego.
What?
Did he actually?
Yeah, I mean, he's not wrong.
What the fuck?
Wait, what happened?
Thumbs are gonna report him.
What I miss?
Wait, is he joking?
What the fuck did you
No,
do?
I'm not. I'm not.
Yes, he is. He's
What did you
Diego.
do?
Everyone.
I'm the guy.
What did you do? Wait, did I hear you say that?
No, Sam. That's not at all. No, Diego was saying. Never mind. I'm not gonna even
Just
say.
text to me in Discord.
I'm so lazy though.
I'm gonna get those cabs. I'm walking over there.
No, it's fine. It's fine. I probably should not say.
Yeah, I'll just take the L. It's not like this is anyway. I'm just bored and waiting the end of the semester. I need something to like spice up my day. Guess I'm this guy.
You guys are
Oh, the pain!
Oh,
I swear to God!
Jack?
What?
Good morning, Jack's rooms after this.
Alright, I bet. I'll buy.
I mean, be honest, you guys. Am I a stupid tween? Be honest here.
Oh,
Sorry. If you want.
wait. Oh, that's much worse than what I was thinking. Holy fuck.
Sure,
This.
just call Aaron Gas.
Chaotic.
Intuition.
Zoom in.
Oh wait, Jordan's also in this chat.
What was that taste?
So.
In that Oh my god. Ooh, that tickles. Stop it.
It's a double prank. I don't see the problem. They're getting pranked 2 different locations.
I'm gonna kick the bucket soon enough, I swear to God.
You're gonna kick the balls.
My more
Kick your balls.
I'm gonna kick the bucket.
I'm gonna kick the balls right now. You know, I haven't done that with someone in a very long time.
Me neither.
AK, it's gonna happen.
So if you kick the balls, half the generation alpha's gone.
Kick everyone in the balls.
Diego, are you secretly Thanos?
I wanna fix it though.
This man's secretly Thanos. He wants to wipe out the rest of Generation Alpha.
What? Oh, I remember why I stopped doing it, because one time I hit someone and nothing happened. Like, what's going on?
You said.
He was like, it doesn't hurt. And
Oh,
I was like,
that's-
what?
You don't need no ability gauntlet, just.
I was ignorant back then. It could have been anything.
Well,
I can't believe Liddy, you have not made it.
I have.
I literally just need one more
Wednesday, so.
Yeah,
Literally wrote me a conclusion in 10 minutes. It took me 2 hours to write the paper.
I want to see this. Wait, yo, God. We just don't want to do some correct. Yeah, just make sure the professor doesn't watch us shrink, because like they can hear it.
There's a for sure a study thing. But I think my roommate said tomorrow is
God
It took me
damn.
like 2 hours to read the intro.
I'm bad at
Just
English.
because I remember I
Well, I mean,
Who sent me this?
tomorrow.
who sent me? Oh, who sent you what?
Somebody did your my photo.
You have AirDrop on?
Yeah.
Turn that off before you get a virus.
I was like, ugh, I guess.
Shit, there's no wood to knock on. It's a run of man's desk and knock
I'll
on
take
it.
them over now.
It's the only wood there is there.
I told it to my brother because my parents didn't buy my graduation pictures for high school. And then I was like, whatever. I
Oh,
had fucked
shit.
up teeth back then. So I was like, buy my college ones. They're gonna be brand new. $5,000 on it. My brother was like, yeah, good thing we didn't buy those other ones. I was like, Photoshop them. Which I've done before.
Sammy's
And I thought it would be fun. Not.
So,
Dude,
Bronson, if you're listening, because I know you're watching
And
the
no one
stream,
noticed,
get the
and no
fuck
one
to the
called me
doctor or
out.
wherever you have to go. This is an order from the surfer owner.
It looks
Go.
pretty good, but like back then, it
Does this figure
was good
look
back
like?
then. I don't remember.
We get for 241.
Oh, he heard it.
Oh, so he did hear. Technique 100. Fine.
Alright, so.
You're pretty much Beethoven at this point. I'm gonna call you Beethoven. $25%. Soon enough, it's gonna be 0.
Let's see this one.
It's a abbreviation.
That's me.
Okay, so let's see if we can see the values of each of them, so we can see why it works if you put the values in either largest first or smallest first. It won't change them. Okay, so if we put in 10 and 30 first, as soon as you do that, it swaps the values because when you do 10 mod 30, the remainder is 30. So then this becomes 30. 30 mod 10 is 10. Or 30, not 30. 30 modded by 10 is 0. So then we return back the one that is divisible into the larger. So let's do it with like 90 and 30. We'll do 90 and 30. We'll get back the answer of 30. Let's do the same number. Let's do 90 and 15, maybe. We'll try a few. So 90 and 15, we should see 90 and 15, and then maybe 15 is the largest. Yeah, I think 15 will be the largest. And then if we do 1590, then we'll see the same thing. We'll see 1590, we'll swap it, and then we'll get back 15 as the answer for our greatest common divisor. But it's just kind of built into the process. So it is one of those good ones that Euclid came up with. So first, the answer just comes right away. But then if we reverse it, we'll see 1590, and then it will state 9015 because when you do 15 modded by 90, then the remainder is 90. So then that value gets put in the first position. That's how we get the correct answer. I've seen some books, like in C, where I don't think that there's an issue because Euclid's algorithm should work the same everywhere, but the reason I even brought it up was a C book I have actually accounts for it in the code where if the first number is smaller than the second number, it first reverses them before it puts it in, but it may have been a different implementation for the algorithm too. You can also implement this using subtraction, but the non-operator is the most common way. So put this as 1590. Okay, so let's just think of one where it's going to go through some more steps so we see some action. Let me look up one that has lots of steps. If you can think of a number, let me know. Just try one of these. 54 and 24? Yeah, let's try that one. Right, so yeah, I think the step one that I'm thinking of is the one that uses subtraction, but it's not the standard one. That's why I didn't do that. Let me see if it shows that one. If this doesn't show, we'll leave it aside because it's not the one that you really want to keep in mind too much. Oh yeah, so here it is. So notice that this one is where you have to account for whether one is larger than the other. So this uses subtraction. So notice that it looks the same, but it accomplishes the algorithm in a bit of a different way. So let me copy this in, and let's try running this as a recursive algorithm. So first we'll have to, well, let's see, is it going to be easy to make it recursive? Yeah, it will be. We'll just have to make, I'll just make it a different space for the algorithm. So call it, this. Okay, so we gotta make this work. So if A equals B, return A. So the base case simply just means you have to have, the method needs to have assurance that you're gonna return a value no matter what happens. So that's what the base case is, but it doesn't have to be to zero. It just has to be, the compiler has to determine that a return is going to happen one way or the other. So that's what's going on. But you saw that I got this randomly off the web, so we gotta make this work first. So we're gonna make if this, then return A. So we gotta get rid of this. I think it was pseudocode, I'm not sure exactly how. Return A. So that'll work. And then if A is greater than B, then return GCD A minus B. So we got to change the variable names to X and Y, but we'll do that after we get the rest of it set up. And then when we print them, maybe we'll see some more of the steps. So let's see. Let's do this. And that. X, Y. So far we're getting there. What's the issue here? Why doesn't it like that? Oh. Is that going to work? I'm going to change A to an X. So let's try it at least. Maybe we'll see the steps, maybe not. But if not, we can look at the paper that was sent. And then we'll do an example review for interface and abstract to change it up a little bit. So we're going to do this. So let's print out. So who wants to guess what the error message is going to be? I have a guess too if nobody guesses. But remember I had said that you have to return a value for whatever method you set up. So with this way, is a value guaranteed to be returned? Do I need to have one more return statement somewhere?
You have to return, I guess, the GCD.
Yeah.
Right.
So, because the base case usually do have a return statement, but then we also have to return in the if else structure, similar to what we have here. So in our original version using mod, at the base case we returned the value, and then in the other case we also returned the method call. So a value is going to be returned. So when we look at the error that's up here, I don't believe the error is with the line itself. I think it's going to, oh no, it'll be with the line itself and also something else. There should be an error for the method. Let's see. This. All right, so that's the error that I was expecting to get. So this should say the method has to return a value because we only have the one return statement. So we'll return GCD x minus y, etc. Let's do okay, so now the error went away. So that's the the thing about any method. You need to make sure that the value that is in the method header is actually returned. So let's see if we can get a view of the steps by printing them out like we were trying to do with the mod dash. So you might have noticed that I didn't use curly braces like I normally do. If I don't use curly braces, I usually put the thing on the same line so that it's obvious that it's connected to the if statements. That's like a way to do it. It makes it clear. But since I need to put in the print statement, now we have to put in some curly braces. Because if we put in this statement, now the return statement will be ignored because only the system call is attached to the end. So we'll say
Live reenactment of the Then it's either both.
Everyone prepare ourselves. We got a fight on our hands.
Thank you, Max.
so let's see what we get.
Yeah, actually, it's just that I didn't like.
Okay, so now we see how it's done. So we got 54, 24, 30, 24, 6, 24, 6, 18, 6, 12, 6. So this shows kind of how the mod operator works algorithmically, like as far as if you read the proof. That's how it gets there, but it does it all in one step because it finds the lowest common denominator using a different pathway. So 54 and 24, we know that I just want to make sure this is correct. 24, 12, 12, I just wanted to make sure that 6 was the correct answer. So 6 is the greatest common denominator between 54 and 24. When we ran this with our mod, I think we just got that 6 right away. Here we see the iteration of the steps. So I guess that's the reason for using the subtraction version to at least look at it. But this isn't Euclid's algorithm per se, because the original one is in Greek, which I don't claim to be able to read, but it's supposed to be closer to the mod than to the subtraction. But both give you the same answer. So let's put 24 first, and then see that we get the correct answer, and then look at the algorithm and see that it actually accounts for it. Okay, so 24 and 54, we still get the correct answer. But now let's go back. Let's go down to the algorithm for the subtraction version, and let's find the place where it says if the first one's bigger or not, and it does something. We'll remove it, and then we'll see if it still gives us the right answer. We'll see that the modulus version is more flexible because it accounts for it in the way that mod works, whereas subtraction, doesn't do that. Okay, so if x is greater than 1, so if 54 is greater than 24, then it's ready, it's all set. Otherwise, then do the one that's put in the else statement. So let's just say, let's comment this out. And let's see if the compiler even notices that might happen. I don't think it will. I think it will be a runtime error. Or it will simply be a logic error if we don't get the right answer. Okay, so we've got, okay, so the compiler has noticed that the way that we've set it up, you might not get an answer return. So the compiler is already stopping us from doing it. So we don't have the opportunity to see what it would look like if we attempted to do something. So in this case, the compiler sees it. And when we look at the mod version, the compiler doesn't throw an error because mod accounts for it. Because again, 10 mod 30 is 30. The numbers reverse by themselves. You don't have to do the reverse operation. Whereas if you use subtraction, you have to do the reverse operation in the code like this. Because 10 and 30, subtraction won't work that way. Mod has it built in where the swap just happens if you try it out for yourself. Okay, so for a review challenge, and this is certainly something that's going to be on the final. say that we've got a driver class, we're gonna have an interface and then a class that uses the interface. So we're gonna quickly write that up because the goal is gonna be, if you wanna look it up or think about it beforehand, the goal will be, given an interface, how do you do the same thing using a class? And what kind of class does it have to be to simulate an interface exactly? That will be the goal.
That's the annoying thing. It's like, bro, just believe me. You have all of it.
Okay, so we've got the class my class, and we're going to have the class with the interface inter one. So we're going to put a couple of methods in inter one. So let's say okay. Okay, so based on the method constructor that's right there, what do you know about this method before we implement it? What's the return type?
It's a string.
It's a string, so it's got to return a string. Let's just leave one, because the principle will be most easily demonstrated with just one thing, so that we do the side by side with which type of class. So now let's use the interface to, so it's, right now it's going to take a string, it's going to return a string, and let's use it in the class my class. So, go to my class. So we're going to say implements inter one. So what is it about interfaces that we're going to see as far as the error message? It's going to say what to us? That we have to, what do I say?
You have to implement methods.
Yeah. So we have to implement the method that returns a string and accepts a string constructor. So we'll just say, so it was public, it had string return type, it was called cat in, and it accepted a string variable. But in this case, we actually have to implement it, so we'll just say return list. Just so that we can get it to work, and then we can change it later to actually do something. But we need to return a string. So now we've implemented the interface correctly. So it's going to accept a string, it's going to return a string. So I guess we would want it to return, just to make it do something, we want it to have the ability to return the string that it accepts. So in order to have this return the string that it takes in the parameter list, what will I change test to? It accepts the string as what variable?
As a string, right? As y.
So we'll return
Y.
y. So let's just try that. So we return 1. So if we call on this and we pass it a string, it'll return the string back, just to demonstrate that it's doing something. So for this, it's not to do anything fancy with what it does, but to, after we get this working in the driver program, the goal will be, how do we do this using a class? What kind of class does it have to be in order to exactly mimic an interface? So we'll go to, so we've still got this. Just before we get on to the driver part, what part of the constructor here is optional, because in interfaces all methods are something and something.
Interfaces, all methods are abstract,
They are.
so the void part is optional.
No, with abstract, so void is the return, is the, oh actually, sorry. That's a different one. But, your answer was right, but I guess my brain likes to use that name for interfaces. So, for this, oh actually, you just said it right there. I left out abstract, so I left it out here already, so we see that abstract is optional. So abstract is optional because all methods in an interface are abstract, so you can put it in or not. But there's one other word here that's optional, because all methods in interfaces are abstract and
Optional.
public. So we can remove public too. However, I would recommend leaving them both in. So this works, but I recommend doing what I didn't do, which was also leave this one out. Because if somebody's reading your code and they need to implement your interface, they see that's the method header, then they just implement it correctly. Public, string concatenate. And this way they just know that this is an abstract method, so they have to implement it. But when you're implementing it, you don't include abstract, or else the whole class has to be abstract. So we go back to our driver class. Okay, so here's driver. So let's make an object of type my class. So in order to make, so here's another easy review question. Just because this will be the kind of thing you'll need to know how to do for the final. If we want to make a my class object in the driver, what is the single line to make a my class object named obj1 that we're going to be able to call on this this method? So we want to make an object called obj1, and the class we want to make it from is from my class, and we want to do it in our driver class. So the standard way to do making an object is class name it, equals new class name again. So to make this object, what would the first word be? My class. My class. So my class obj1 equals, and then the next word would be new. And then again, my class again. And here we would put in anything that go in the constructor parameter list, but we didn't even have a constructor in our my class. So if we put a semicolon here, we notice that we're allowed to do this. And we're allowed to do this because my class made what for us? Jack? Default constructor. So in the my class, if we did not include any type of constructor, it's as if we had written public my class. So without having written that, if we don't include one that has different parameters in the parentheses, that's made by the compiler. If you make an alternative constructor, then you have to include this because it will not make the default constructor for you. but otherwise it gets made for you. So we want to call on concat me. So
Professor?
we'll go back to our, yeah.
I have an error here. Like I did everything that was shown here, but I still have an error.
In which line?
Like in like line 2, like it says like is this an error? Like it says must implement the methods even though I did.
Well, just check the method name. So did you put in public string concat me with a capital M? Rest
Unless
lowercase.
I'm seeing things.
Well, if it still doesn't work, I recommend deleting it and retyping it. Because if your eyes won't see it, your fingers will see it correctly when you retype it. It happens to me enough time. It's like my strategy. You got it? Jack.
Pass on
What? Please. So let's call on concat. So we go to our driver, and we've got our object that we have just made. So this little message is just saying the object is used there. So we're going to say obj1 dot. And now we get the method list that's available. So if you've written any methods yourself, it's always at the top of the list. So we can call on concat me string. So when we pass it a string, it will return a string. So since it doesn't print anything, we'll have to wrap this up in a print statement in order to print it. And then we'll make the class that mimics this same view. Okay, so we're passing it the string hello. It's going to return back the string hello. So let's actually see that it does, because this way it could look like just printing out the string. Let's make our method add it to itself. It does something. So it's, so let's just say, let's return y plus y. Okay, so returning y plus y simply concatenates the string. So it'll be whatever the string is, no space, and then the string repeated. So we'll see that it actually did something. Okay, so we passed it a string, it concatenated it, it returned back the concatenated string. So now the question is, which is pretty close to a final exam question, given this interface, so the only thing that you really need to change is this right here. Because when you've set up a program where you have a driver class, a class that uses an interface, and the interface itself, if all you do is change that it's going to use a class instead of an interface, everything should still work, because the type of class we use has the same requirement that the interface does. So what's the equivalent of an interface? Which kind of class? That's it. So is a regular class the same as an interface? Like, which class has the property that if you include abstract methods, you have to implement? A regular class?
Not the regular class.
Which kind of class? That uses abstract?
Can you give me a hint?
Well, if you're including an abstract method in this class, which keyword would you maybe use? Think more abstract. Abstract. So, abstract. So, you have to use abstract in the class definition because only abstract classes may contain abstract methods. So we'll make a class that we'll call class 1. This is inter 1 for interface we'll make. And then we'll see the only real difference between abstract classes and interfaces. Okay, so we're going to say abstract class. Okay, so the only difference between an abstract class and an interface is that abstract classes can contain regular methods, whereas interfaces cannot. But if you want to mimic an interface exactly with an abstract class, you simply include all the abstract methods and no regular methods, and then they will be one and the same as far as their behavior. So if we go to our interface, and this will be the same thing on an exam environment. So notice that we have this abstract method definition. It will be done the same exact way in the abstract class because you define them both the same way, with a semicolon, etc. And the reason that I said leave the public and abstract in there is that if you ever need to change it from an interface to a class, you can just copy the method definition over and it works, just as it is. So if we copy this to our new class and drop it in, we see that it works. And then if we go to our class, my class that's currently implementing inter1, we're going to have it use this instead, but the effect will be the same. But whereas we use the word implements to implement an interface, whenever you're having one class inherit from another, the word is wrong.
Implement.
The other way.
Sorry, can you repeat the question?
When you want to have one class inherit from another one, it
Inherits.
extends. So we're going to say extends class 1. So we go to our class, and instead of implements, so if we put in my class, this says, I've not seen this message. Cycle detected. My class cannot extend, implement itself. Oh, I'm trying. Yeah, I use it wrong. That's why I got the interesting message. So I'm going to say class. I want to see if it gives us a hint. The type class 1 cannot be a super interface of my class. Right, so it's essentially saying you're trying to do something with an interface, so we need to say extends. So we'll change this to extends. And now that is I copied the wrong order. That's why. Okay, all right, so the reason that there was an error was that I had copied the wrong abstract method from a very similarly named interface. So notice that there's no error because this will still work just the same as it did with the interface. But if I comment out this implementation of concat.me, it will give the same type of error message. It will say that you need to implement the inherited abstract method concat.me from class 1, just like it would tell you if you hadn't done it from the interface. So we do this, this. This says, must implement the inherited abstract method. Same thing from a class or an interface, they're both abstract. And since we don't have any other methods in our abstract class, the interface and the abstract class are equivalent. That's what I was meaning by the equivalent between the two. So let's just run it to show that it still works. And then that will be that. So we see they still work. So So this I will also, I'll put up to Blackboard in addition to, I'll leave all these up in my Eclipse.
It's
folder.
on Blackboard?
No, I'll put all these up on Blackboard from the Eclipse tab list after class. So that this one will be in there and all the rest, the GCD and the subtraction, etc. But, you know, again, the thing to notice is that the interface is, this one. The interface, Inter 1, is the same as our abstract class because they both contain an abstract. And then the implementation requirement is the same because if an abstract class contains an abstract method, you have to implement the method. But then the only difference is, this will be the last thing. Our abstract class, class 1, say that we had not included any type of abstract method, and we just said public. So if we put in a fully implemented method into our abstract class, now it's no longer equivalent to an interface because an interface cannot contain an implemented method. So that's the difference. But as long as they both contain all the abstract methods, they're the same. So there we go. I will also leave this in and I'll put a comment about. I'll comment it out and then I'll leave this one commented. Explaining that if this one is in there, then it's not abstract. Then there's more than one method, one of them being not abstract, and it's not equivalent to our interface Inter 1. So I'll say class 1 and Inter 1 are equivalent otherwise. So that's it. I'll be at office hours, and again, if you weren't in early for the exam, you can bring an electronic device so you can compile, hopefully. But at the very least, you can search the PowerPoint document review sheet because it's a lot faster and more accurate than using your eyes to search. So please have something.